We move on to rocket motion. Consider a chamber without a nozzle like this, and you have gas, heated gas inside. So the gas molecules will be pushing on all parts of the surface. The net force in any specific direction is equal to the net force in any other direction, so there will be no motion. But consider the same situation after we have an opening here. If you have an opening, then the gas will be ejected from this opening, and this way, to conserve momentum, action, reaction, pair of forces, to conserve momentum, momentum before equals momentum after. If the gas is moved this way from this opening, then the rest of this chamber will move in the opposite direction. This is exactly how rocket engines function. I hope you understand it. So you have the nozzle from which gases will go out. As a result, to conserve momentum, if the gases are pushed downward, then the rocket is moving forward. As simple as that. This is the rocket engine. The physics is simple. Just apply conservation of momentum. So before, you have two situations, before and after. Before, you have the mass of the rocket and the ejected gas, okay, with some velocity. After, you have the ejected gas with its own velocity and the rocket now with a new velocity equal to the original velocity plus the change in the velocity. Okay? To conserve momentum, m delta v for the rocket is equal delta m for the ejected gas multiplied by the ejected gas velocity. They are in opposite directions, of course. The ejected gas goes to the left, for example, the rocket goes to the right, as simple as that. So you can solve for the final velocity, the change in velocity, delta v, final velocity minus initial velocity from the conservation of momentum is equal to logarithm m initial divided by m final multiplied by the velocity of the ejected gas. M final is equal to M initial plus the mass of the ejected gas, delta M. Very simple formula, but allow us to understand how rockets function. Okay. So the thrust on the rocket is defined as the force exerted on the rocket by the ejected exhaust gases. If we divide our momentum conservation expression by delta T, okay, to get the force, m delta v, this is the change in momentum divided by change in time. This is the average force. So this is equal to minus velocity of the ejected gas, the change in mass divided by delta T. And the instantaneous thrust is just mass by acceleration. So from this equation, we get this solution for the instantaneous thrust. A 100-gram lump of clay hits a wall at 70 centimeters per second and sticks. A 100-gram rubber ball hits the same wall at 60 centimeters per second and rebounds with a speed of 30 centimeters per second. Which object experiences the larger impulse delivered by the wall during the collision? So you have to take the initial momentum, you have to take the final momentum. The change is equal to final minus initial. So for the rubber ball, it would be 30 minus 60, right? So the change would be 30 m plus 60 m, so it's 90 m. M is the mass, while for the clay it is just 70. So naturally the ball will have the greatest change in momentum and therefore the larger impulse. Cart A with momentum P in magnitude collides with cart B at rest and rebounds. What can you say about the momentum of cart B after the collision? So after the collision, B will move to the right and A will move to the left. You need to conserve momentum. So total momentum after collision equals total momentum before collision. Okay. So this way it is larger than P because the change in momentum, you have P minus P, for example. So it's 2P, the change in momentum. To conserve momentum, the change here is 2P, the change here must be 2P. So the momentum of this cart will be greater than P. Two blocks M equals 2M sit on a horizontal frictionless surface with a compressed massless spring between. After the spring is released, the mass M, this one, has velocity V. The total energy initially stored in the spring was. So here you need to conserve energy because we are told it is a frictionless surface. Frictionless means there is no loss of the energy due to friction. So energy was originally potential elastic energy stored in the spring, and after they were released, the energy now is converted from elastic into kinetic energy. So in this case, after collision, we are told that M moved with velocity V, so the kinetic energy will be half mv squared, half mv squared. Since m is equal to 2m, m uppercase equals 2m lowercase, so you have factor 2, you have factor 1/2, you end up with this energy mv squared. Then to conserve momentum, the smaller mass must be moving twice as fast as the bigger mass, because of this factor m equals to m. So the final kinetic energy, half m multiplied by 2v squared, which we get from the conservation of linear momentum. 2 squared is 4. You have 1/2 here, you cancel 2 to 4, you end up with 2mv squared. That would be the kinetic energy of the smaller mass. When you add the two kinetic energies, they add to 3mv squared. That is the total kinetic energy after the system released, and this is equal to the original energy that was stored in the spring. We are done with this chapter. Just to go over the fundamental things that we learned. We learned that momentum is the product of mass by velocity, and impulse is the product of force by action time. We learned that impulse is equal to the change in momentum. You cannot change momentum without a force and time, which is impulse. So we always need impulse to change the momentum. Then conservation of momentum is always applied for all kinds of collisions. We have three main types of collisions: elastic, inelastic, and perfectly inelastic. For elastic collisions, momentum and kinetic energy are both conserved. For perfectly inelastic and inelastic collisions, only momentum is conserved. For a glancing collision, you have to deal with x and y momentums and to apply the conservation of momentum for both directions. We learned about the rocket propulsion, how rocket engines functions and how to calculate the instantaneous thrust.